Bismillah ar-Rahman ar-Rahim, rational function. In this lecture, we shall define the rational function, determine its domain, and recognize the asymptotes, which are the base or pre-step of plotting the graph of the function curve. Definition of rational function. If p of x and q of x are two polynomials, then the function f of x given by f of x equals p of x over q of x is called a rational function. This means if we have two functions, both are polynomials, and we put one of them in the numerator and the other in the denominator, then we have created a rational function. But what is a polynomial? The polynomial is a sum of several terms that contains different powers of the same variable. Again, the polynomial consists of term, etc. Each term is a combination of some factors containing a number and variable. That is the number and that is the variable. And this variable is raised to some power. The greatest power determines the degree of the polynomial. For example, if the greatest power n here, if n equals 3, the polynomial named a third degree polynomial. If n equals 2, we get second order polynomial, which is called, as we know, quadratic function. By the way, the first order polynomial called linear function, and zero order polynomial is a constant function, because 0 over x make x to the power 0 equal 1, so p of x equal only the constant an. Now we have defined the rational function, and about its domain. The domain of f of x is the set of all real numbers except those for which q of x equal 0. That's because we have a numerator and a denominator, and the problem always comes from the denominator, which should be not 0, because 0 as a denominator makes undefined functions. So from this concept, we have defined the domain of the rational function, all real numbers, except the numbers which make the value of the denominator equals 0. About the graph of a rational function may include a vertical asymptote and or a horizontal asymptote. What is asymptote? An asymptote is an imaginary line, mostly straight line, that a curve approaches as it moves towards infinity. The curve visits these asymptotes, but never overtakes them. In rational function, we may have vertical and or horizontal asymptote, means the rational function may have only one vertical asymptote, more than vertical asymptote, horizontal asymptote, neither vertical nor horizontal asymptote. All these depend on the definition of vertical and horizontal asymptotes and how to calculate or find out both of them. This is the main point of studying the rational function. Let's first define the vertical asymptote. If the line x equal a is a vertical asymptote of the graph of the function f, provided f of x tends to infinity or f of x tends to minus infinity as x approaches a from either the left or the right. This means that if the function, the curve of the function, goes to infinity or negative infinity when x approaches a from right or left, then we have a vertical asymptote whose equation is x equal a. And the definition of the horizontal asymptote will exchange the function and the point. Let's see. The line y equal b is a horizontal asymptote of the graph of the function f, provided f of x tends to p as x tends to infinity and or x tends to minus infinity. Here the point and the function exchange. Here the function tends to infinity, here the function tends to p. Here x approach a, here x goes to infinity. Okay. Note that, and take care, the equation of a vertical asymptote is x equals, and the equation of horizontal asymptote is y equals. Vertical, x equals. Horizontal, y equals. And now let's show this example. G of x equals x plus 1 over x minus 2. First, let's plot the graph. There are many programs for drawing the function's curve. One of them gave the following curve. We can check the graph first. Put x equal 5, so 5 plus 1 over 5 minus 2, so 6 over 3 give 2. So at x equal 5, we get 2. Correct. Another point, x equal minus 1. Minus 1 gives x g equal 0. So at x equal minus 1, the function equal 0. Okay, correct. Now, we can note that curves goes to negative infinity as x approach 2 from left, and goes to infinity as x approach 2 from right. This means that the function has a vertical asymptote at 2, and its equation x equal 2. And about the horizontal asymptote, we see that the curve approaches 1 at x at positive infinity x from up and negative infinity from down. This means that the function has a horizontal asymptote at 1 and its equation y equal vertical x equals 2 and horizontal y equal 1. This example shows only the asymptotes, but it is your task to find out or calculate both of the vertical and the horizontal asymptotes. So we must recognize the rules of calculation. Start first by vertical asymptote. If the real number a is a 0 of the denominator of the function f of x equals p of x over q of x, provided that p of x and q of x have no common factors, then the graph of the function has a vertical asymptote x equal a. In other words, the values of x that make the denominator is 0 assign the vertical asymptote. So simply you can find the value or the values of x which makes the denominator equal 0 by, which is called, by the way, the roots of the function. We can easily find them by solving the denominator for x. You can use calculator for that. And by solving the denominator, the values you have got give the equations of the vertical asymptote. The next example shows how it is easy to do that. Example 1. Find the vertical asymptotes of the rational function f of x equals x cubed plus 1 over 2x plus 7. Note that after looking for the common factors between the numerator and the denominator and then simplify the function, don't deal with the numerator. You are only concerning of the denominator. Let's see the solution. By solving the denominator, we get x equal minus 7 over 2. 2x plus 7 equals 0. 7 to the right minus 7 over 2. So x equal minus 7 over 2. There is 0 at x equal minus 7 over 2. And with looking at the function, there is no common factor with numerator and or between the numerator and the denominator. Finally, the vertical asymptote is x equal minus 7 over 2. If we put this function on a plotting curve program, we can just see the vertical asymptote. Here it is clear that as x approaches minus 3 from right, the curve goes to negative infinity. Look, minus 2, minus 3, minus 4. So here is the vertical asymptote. And its equation is minus 7 over 2. Let's see another example. Find the vertical asymptotes of each rational functions. A, if x equals x cubed over x squared plus 1. B, g of x equals x over x squared minus x minus 6. Again, after simplifying the function by eliminating the common factor between numerator and the denominator, you deal only with the denominator. This example has two parts. The first one is a rational function with denominator x squared plus 4. This denominator has no zeros, means there is no value for x makes the denominator equal 0. This is clear by solving x squared plus 4 equals 0. By transferring 4 to the right side, we get x squared equal minus 4. No, there is not any value can be multiplied by itself to give minus 4. Also, if you solve this equation using the calculator, you will get x equal plus or minus 2i. I is an abbreviation for imaginary. This means you can imagine that there are two values, plus 2 or minus 2. But in fact, there is not any real value of x. Therefore, the denominator x squared plus 4 has no real 0. So the graph of f has no vertical asymptote. Put this function on a plotting curve program. You can see that there is no any vertical asymptote. And in the second part of the example, the denominator x squared minus x minus 6 has zeros of 3 and minus 2. The numerator has no common factors with the denominator, so x equals 3 and x equal minus 2 are both vertical asymptotes of the graph of G. Of course, it is very easy to solve the denominator by factorization or by calculator to get x equals 3 and x equal minus 2. Any of these two values makes the denominator equal 0. You can check it simply. And also, these two values are the equations of the two vertical asymptotes we have. The plot of the function curve shows that at x equals 3, here the first vertical asymptote, and its equation x equals 3. And here the second vertical asymptote at x equal minus 2 and the equation x equal minus 2. Finally, the values of x which makes the denominator equal 0 give the vertical asymptote. The other part is how to find out the horizontal asymptotes. Let f of x equals an times x to the power n plus an minus 1 times x to the power n minus 1, etc. over pm times x to the power m plus pm minus 1 times x to the power m minus 1, etc. be a rational function with numerator of degree n and denominator of degree m. 1. If n less than m, then the x-axis, which is the line given by y equals 0, is a horizontal asymptote of the graph. 2. If n equal m, then the line given by y equal an over bm is the horizontal asymptote of the graph. 3. If n more than m, the graph has no horizontal asymptote. That is because there are only 3 possibilities about the relation between n and m. n less than m, n equals m, n more than m, where n is the largest power of the numerator and m is the largest power of the denominator. So, first of all, we have to arrange the two polynomials decreasingly. The possibility n more than m gives no horizontal asymptote, but the others give. Therefore, to get a horizontal asymptote, the degree of the numerator must be less than or equal that of the denominator. n less than m gives y equals 0 as a horizontal asymptote. n equals m gives y equal an over bm as a horizontal asymptote. So your task is to investigate the degree of the numerator and the denominator to determine the equation of the horizontal asymptote. It's very easy task. Let's show this example. Find the horizontal and the vertical asymptotes of the following rational functions. A. F of x equals 2x plus 3 over x squared plus 1. B. G of x equals 4x squared plus 1 over 3x squared. C. H of x equals x cubed plus 1 over x minus 1. This example teaches you how to determine the horizontal asymptote. I make it blue. And this example also is a revision of the vertical asymptote. I make it green. For part A, about the horizontal asymptote, the degree of the numerator is less than the degree of the denominator. Therefore, the equation of the horizontal asymptote directly is y equals 0 or x-axis. About the vertical asymptote, as we mentioned before, we deal only with the denominator. This equation has no solution, or there is no zeros for the denominator. Hence, there is no vertical asymptote. The graph shows no vertical asymptotes, but the x-axis is the horizontal asymptote. Here it is blue, and its equation is y equal 0. Part B, the numerator and the denominator are both degree 2. The line y equal 4 over 3 is the horizontal asymptote. Here, 4 the factor of x squared of the numerator, and the 3 is the factor of the x squared of the denominator. So y equal 4 over 3 is the horizontal asymptote. Very simple. And the denominator has a 0 at x equal 0. If x equals 0, the denominator equals 0. So here there is one vertical asymptote. Its equation is x equal 0. So there is a horizontal asymptote at y equal 4 over 3, and its equation y equal 4 over 3. Make it blue. And x equals 0, y-axis, I make it green, is a vertical asymptote. Okay. The last part, part C. The degree of the numerator is larger than the degree of the denominator. The graph of h has no horizontal asymptote. Okay. And the denominator has a 0 at x equal 1. So x equal 1 is a vertical asymptote. And this is the graph. No horizontal asymptote. And at x equal 1, there is a vertical asymptote. Finally, we have defined the rational function as a ratio consisting of a numerator and a denominator. Both is a polynomial. The domain of the rational function is all real number except the zeros of the denominator. And by determining the vertical and the horizontal asymptotes, we can put the guides of the graph of the function. Thank you, and please wait for the next lecture in which you can recognize the exponential function.